If something is visiting Earth, it has a home address. For over 60 years, 4 star systems have surfaced again and again in UFO lore: Zeta Reticuli, the Pleiades, Sirius, and Tau Ceti. Each arrived on the list through a completely different door: an abduction sketch, ancient myth, tribal astronomy, a radio telescope. But when you hold those names against what modern astronomy actually knows, only one survives as a serious candidate. On September the 19th, 1961, Betty and Barney Hill were driving through New Hampshire's White Mountains when they observed a strange silent craft. Under hypnosis years later, Betty recalled a 3-dimensional star map shown to her by the vessel's occupants. She drew this pattern from memory: a cluster of 12 stars connected by solid and dotted lines. In 1964, an amateur astronomer named Marjorie Fish spent years building physical models of nearby star positions to find a match. Her analysis pointed directly to a binary system known as Zeta Reticuli. This single claim transformed the UFO phenomenon from vague lights in the sky into a specific search for a home address. For the first time, a reported close encounter yielded a concrete stellar destination, making Zeta Reticuli the baseline origin story for modern extraterrestrial lore. Yet, this map exists entirely within the realm of eyewitness testimony and creative reconstruction. No physical evidence links this system to Earth. The map remains a fascinating piece of cultural folklore, the moment humanity's search for others focused on a real point in space. The Pleiades, a bright cluster in the constellation Taurus, carried thousands of years of mythological weight before Swiss contactee Billy Meier claimed encounters with its inhabitants, publishing color photographs of alleged spacecraft in the late 1970s. Sirius, the brightest star in the night sky, gained mystique through reports of the Dogon people of Mali. In 1976, author Robert Temple popularized the claim that the tribe's knowledge of the invisible companion star, Sirius B, came from advanced visitors from that system. Tau Ceti, however, entered the narrative through science rather than folklore. In April 1960, radio astronomer Frank Drake launched Project Ozma, pointing the Green Bank telescope at Tau Ceti to search for artificial radio signals. Drake's experiment gave the star an enduring credibility in the search for intelligent life. These 4 star systems are not random points on a map. They represent different human pathways to cosmic meaning through ancient myth, controversial modern photographs, and pioneering science. This recurring pattern raises a natural question: what do we actually find when we look at these distant coordinates with modern technology? Astronomers catalog Zeta Reticuli as a wide binary system located 39 light-years from Earth. Established data confirms both stars, Zeta 1 and Zeta 2, are G-type solar analogues, sharing a similar mass and temperature with our own Sun. However, despite decades of high-precision radial velocity surveys, there are no confirmed exoplanets orbiting either star. Any claims of habitable worlds here remain entirely hypothetical, as observational limits have ruled out large gas giants and found no trace of smaller rocky planets. By contrast, the Pleiades presents an even more hostile environment for potential life. Located roughly 440 light-years away, this iconic open cluster is incredibly young, active for only about 100 million years. Established astronomical measurements show the cluster is dominated by massive, hot B-type stars that flood the surrounding space with intense ultraviolet radiation. No planets have been detected within the cluster, and the extreme stellar activity makes the development of stable, temperate planetary environments highly implausible. This side-by-side evaluation reveals a stark disconnect. The cultural fame and easy visibility of these star systems do not correlate with planetary habitability. While one system consists of sun-like stars without planets, the other is a cosmic nursery too young and violent for life as we know it. Stripping away the romantic assumptions of modern lore, the physical reality of these coordinates challenges their status as likely origins for interstellar travelers. Sirius, the brightest star in the night sky, lies just 8.6 light-years away. Though culturally prominent, its physical environment is hostile. The primary star, Sirius A, is a hot, luminous star orbited by Sirius B, a dense white dwarf. Their eccentric 50-year orbit creates severe gravitational disruption and floods the surrounding space with intense radiation, leaving little hope for stable, temperate planets. To evaluate such systems, science relies on a strict yardstick of potential habitability. For a planet to support life as we know it, it must possess a rocky surface with a mass between 1/2 and 5 times that of Earth, hold a stable atmosphere, and orbit at a distance where liquid water can persist on its surface over geological timescales. Tau Ceti, a sun-like star just 12 light-years away, matches this standard. Unlike the chaotic Sirius system, Tau Ceti is an ancient, magnetically quiet star. Astronomers have confirmed multiple low-mass planets in its system, including worlds orbiting directly within the conservative habitable zone where liquid water could exist. Yet, suitability is not proof. A habitable zone only indicates the physical capability to host life, not the presence of life itself. While Tau Ceti stands as the most scientifically viable candidate on our short list, the question of whether anyone actually looks back from its planets remains completely unanswered. Even the closest candidate stars present a staggering barrier: distance. Tau Ceti lies 12 light-years away, meaning a spacecraft traveling at the speed of our fastest current probes would take over 200,000 years to arrive. To make such a trip practical, any advanced civilization must bypass traditional propulsion entirely. This shifts the focus from where these visitors originate to how they could physically cross the cosmic void. Theoretical physics offers potential shortcuts, though they exist strictly on paper. In 1994, physicist Miguel Alcubierre proposed a warp drive concept that bypasses the cosmic speed limit by contracting space-time in front of a craft and expanding it behind. Other theorists suggest traversable wormholes, shortcuts through the fabric of space itself. Yet, the physics keeping these concepts open also presents major barriers. Building a warp bubble or stabilizing a wormhole requires exotic matter with negative energy density, a substance not known to exist in the real world. At the same time, manipulating space-time on this scale demands energy equivalent to the mass of entire planets, while creating serious risks of causality violations. For now, these cosmic shortcuts remain mathematical possibilities, not engineered realities. To move beyond anecdotal claims, researchers rely on a strict checklist of physical criteria. If an advanced technology is traveling from these target stars, its presence should generate observable traces. Scientists actively search for specific technosignatures, such as narrowband radio beacons or nanosecond laser pulses. A physical craft utilizing high energy would release detectable mid-infrared waste heat or emit high-energy gamma-ray flashes during transit. Its trajectory across our solar system would exhibit rapid, non-Newtonian acceleration that violates known laws of orbital mechanics. Yet, systematic searches have yielded no such markers. Targeted radio observations of Tau Ceti and Zeta Reticuli have detected no engineered signals. Wide-field infrared surveys have found no anomalous thermal signatures, and astrometric tracking records no objects performing impossible maneuvers. The boundary between science and speculation is defined by these testable signals. Until a verifiable physical trace is recorded, these systems remain silent, leaving the question of extraterrestrial visitation open to individual judgment. Today, the gap between cosmic myth and scientific reality is narrowing. The question is not just which star system hosts life, but whether our understanding of physics is ready for what we might find. What do you think lies in the deep void? Share your thoughts below.